As we mentioned previously, the scientific method is heavily dependent on measurements. And for this reason, we've developed an extensive set of units for measurements. And what are units? Units are a label that basically tells us what is being measured. So that's what units are all about, and that's really important. Obviously, you need to know when you see a number what that number refers to. So all measurements, all numerical measurements have at least three parts. They have a number, which is sometimes referred to as the magnitude of the measurement, an error that results in what we call uncertainty, and we mentioned the term uncertainty when we were talking about scientific notation, and units. So this number here, that tells you the size of your measurement. The unit label tells you what is being measured. And then this number here, which is a measurement of the uncertainty, that's really telling you that the temperature is somewhere within 0.2 of this number. So it's somewhere between 27.3 and 27.7 degrees Celsius. Somewhere in there is the true value for today's maximum temperature. So, if you look at the label, in this case, it was the label on a medication, which was an antihistamine. You'll see a whole kind of variety of different measurements here. It tells you in different units. It tells you to take 2 tablets. There, the unit is tablets. And then we've got hours. That's a measure of the unit of time, and so forth, right? Okay. So, that's what's going on there. So we've got 2, and up here we've got the unit of mass, right? So there's 3 different units at least. Here we got some temperatures, degrees Celsius and degrees Fahrenheit. So you can see there's a whole variety of measurements there. So these unit labels tell us what is being measured. If we see gallons, we know that volume is being measured. If we see miles, we know that it's length that is being measured. Now, in science, we use the International System of Units. And this was developed in France. It's called Le Système International de Units. And so for that reason, we'll often talk about using the SI system of units from Système International. Okay? So what is this? Well, it's basically the modern version of the metric system. So why do we like the metric system over traditional units? Well, the reason is because the relationship between different units are always powers of 10. So in the metric system, you see we have these 2 units of length, one being centimeter, one being meter, and the relationship between the two is just simply a power of 10. In the English system of units, we have 2 units of length, one being the foot, one being the inches, and you can see the relationship between them is not a power of 10. Now, most of us know that 1 foot is 12 inches, but if I was to ask you something like, how many inches in a mile, then it starts getting weird, right? People forget because it's difficult to remember these conversions when they are not a simple multiple of 10. So if we go for something like volume, in the metric system, we can relate milliliters to liters via simple power of 10. In the English system, we know that 1 gallon is equal to 4 quarts, but if I was to ask you something like how many cups in a gallon, or how many teaspoons in a gallon, most people wouldn't know because these conversion factors are difficult to remember because they're not simple powers of 10. So that's the advantage of the metric system over traditional units of measure. So the International System of Units has 7 base units. For length, the base unit is the meter, and it has the abbreviation lowercase m. For mass, the base unit is the kilogram, and that has the unit abbreviation lowercase kg. For time, the base unit is the second, and it has the unit abbreviation lowercase s. For temperature, the base unit is Kelvin. Because it's named after a person, it has unit abbreviation uppercase K. The amount of a substance, the base unit is the mole, and that has abbreviation all lowercase mol. Now, I just want to point out that these two we won't be using till near the end of the general chemistry sequence. In fact, luminous intensity we probably won't use at all. But electric current has the base unit of the ampere. It's named after a person, so its abbreviation is uppercase A. And then luminous intensity, which is how bright a light is, has the unit name candela, and that has the abbreviation all lowercase cd. Now, when you think about this, we've only got 7 base units. There are many more than 7 things that we could measure. For example, it's pretty easy to measure the surface area of something, or to measure the speed of something. But to get these extra units, what we call these derived units, we're just going to mix and match the base units, right? So if I wanted something like an area, well, area is, the area of a rectangle is just the length of each of the sides multiplied together. So, it's length 1 times by length 2. And so length 1 would have units of meters, length 2 would have units of meters, and so multiplied together would give me units of an area being meters squared. Speed is defined by distance over time, so the base unit for length or distance is the meter, so that would have units of meters, and then the base unit of time is the second. So in the SI system, we might use units of speed as being meters per second. Okay, so when we have one thing written on top of the other, we're going to pronounce that kilogram per meter. Okay. All right. Now, in chemistry, as we mentioned before, when we were talking about scientific notation, we're often dealing with very large or very small quantities. And to help us write out these quantities, a system of what we call metric system prefixes has been developed. And what these are letters that substitute for multiplying by a power of 10. So these are 6 of these metric system prefixes that you need to memorize for general chemistry. We got mega, kilo, deci, centi, milli, micro. Every prefix has a name, which is just a word. It also has a symbol, which is either an uppercase or lowercase letter. Normally it's an English letter. One of the common ones does have a Greek letter. So micro has for its symbol the Greek letter mu. Okay, sort of is read as mu, mu. And then the letters substitute for multiplying by a particular power of 10. So mega means multiply the number by 10 to the 6. Kilo means multiply the number by 10 to the 3. Deci means multiply the number by 10 to the minus 1. Centi means multiply the number by 10 to the minus 2. Milli means multiply the number by 10 to the minus 3. And micro means multiply by 10 to the minus 6. So if I write 1 kilogram, what that really means is 1 times 10 to the 3 grams, and of course we can skip the writing 1 if we want to. 1 centimeter, what that really means is 1 times 10 to the minus 2 meters. So the letter is just substituting for writing out multiplying by a particular power of 10. 1 micrometer means 1 by 10 to the minus 6 meters, because micro means multiplied by 10 to the minus 6. So that's how they work. If I have 2 centimeters, what does that mean? That means 2 times 10 to the minus 2 meters, right? If I had 5.1 micrometers, what does that mean? That means 5.1 by 10 to the minus 6 meters. So you see, it just is a little shorthand rather than having to write out these powers of 10. Now, there are a lot of these metric prefixes, or these SI prefixes more exactly, and you don't need to have all of them memorized. There is a table in your book, and you can kind of just copy that over into a Word document, but it is worth having one of these kind of tables on hand. Some calculators have these tables built in. So for every prefix, there is a name, there's an abbreviation, and then there's, what it means, right? So what the multiplicative factor is for the prefix. Like I said, in Chemistry 139 online, every quiz, test, final exam is open notes. So you might want to think about having one of these sort of like elaborate tables available when you're sitting your quizzes or your tests. Okay, so let's kind of try and get a little kind of a bit of a feel for how big these quantities are. So the base unit of mass in the SI system is the kilogram. A kilogram is a little more than 2 pounds. It's 2.2 pounds. And what does that kind of like, feel like? It's about the mass of a quart of milk. Now, a kilogram is like a lot of stuff. And typically in the chemistry lab, we're not going to be working with kilograms of things. Generally in the chemistry lab, we're going to be working with either grams or milligrams of substances. So that's what we're going to be kind of typically working with. The balances that we use in the chemistry lab can measure down to 3 decimal places in grams. So that gives you kind of some idea as to how well we can measure the masses of things in the chemistry lab. Okay, the base unit of length in the SI system is the meter. I think officially, because it is a French-based system, we're meant to spell meter in the French style, RE as the ending, but if you spell it in the US style, then no one's going to call you out on it. It's completely okay. I think either or is fine, whatever you prefer. And how big is a meter? It's actually about a yard. It's a 9% bigger than a yard, but it's about a yard. And if you don't know, if you want a kind of an image, a yard is about the length of a baseball bat. So 1 kilometer, that's the same as 10 to the 3 meters. 1 centimeter, that's the same as 10 to the minus 2 meters, and so forth. Now, one unit of length that we commonly will use in chemistry later on is the nanometer. At this point, you're not expected to know what the prefix nano means times 10 to the minus 9, but we're going to be using that a lot later on. We'll also probably use pico as well, and that's kind of handy. So I think pico is times 10 to the minus 12. So they kind of do get used later on, but you don't need to know them right now. Okay, now so we did mention that in the SI system, the base unit for temperature is the Kelvin. But commonly, we're also going to see the Celsius system used for temperatures. And in everyday life, we might see the Fahrenheit system used. So in the lab, we commonly use the non-SI system of of Celsius units for temperature, because it's kind of like gives numbers that are like between sort of like 0 and 100. But for calculations, because the base unit is the Kelvin, we'll often use Kelvin units when it comes time to do some math. So an important skill is to be able to convert between Kelvin and degrees Celsius. Fahrenheit is very, very rarely used by scientists and engineers. It's just not a very good temperature scale for the kind of work that we're doing. But you will encounter it in everyday life. Now, converting between the three commonly encountered systems of temperatures requires the use of these formulas here. So you'll want these formulas on hand when you're doing your quizzes and your tests and your final exam in case you need to convert. So they look quite complicated, and we'll go through a little explanation of why they take the form that they do. So the Fahrenheit scale has a different 0 point than the Celsius scale. The two scales are offset by 32 degrees. So on the Celsius scale, water freezes at 0 degrees Celsius, but on the Fahrenheit scale, water freezes at 32 degrees Fahrenheit. Now this is a little weird, because if we consider any of our other scales other than temperature, all of the scales have the same 0 point. So if I have an object that weighs 0 kilograms, it also weighs 0 pounds, right? Now, if I look at something like length, right? If the length of my object is 0 meters, the length of my object would also be 0 feet. Similarly, if I have something like time, if I'm at time equals 0 seconds, I would also be at time equals 0 hours. So these two scales of temperature are a little weird because they don't have the same 0 point. Now, the other thing that is awkward about these two scales is the size of a Celsius unit is not the same size as a Fahrenheit unit. It's a little bigger. You can see that on the scale there. And on the Celsius scale, water boils at 100 degrees Celsius. That means that there are 100 Celsius units between the freezing point of water and the boiling point of water. Now, on the Fahrenheit scale, water boils at 212 degrees Fahrenheit. And that means, if you do the math, 212 minus 32, that there are 118 Fahrenheit units between the freezing point of water and the boiling point of water. So what we're really saying is that in the space of 100 Celsius units, we get 180 Fahrenheit units. That is, a Celsius unit is bigger, and you can see that on these scales here, than a Fahrenheit unit. So there's two things going on. A Fahrenheit unit is smaller than a Celsius unit, and we have to correct for that. And the Fahrenheit scale and the Celsius scale are offset by 32 degrees, and we need to correct for that. So if you work through the math, which I won't bore you with, you end up with these formulas for interconverting Celsius and Fahrenheit. Now, I do want to give you a little bit of a heads up. Sometimes we're just interested in how the temperature changes. We don't care about the absolute value. To indicate a change, we're going to use a delta. That means change. And the change in a temperature in degrees Celsius is equal to 5 on 9 times the change in degrees Fahrenheit. Okay, so if you're only interested in how the temperature is changing, you don't have to worry about the offset of the 32 degrees. Similarly, the change in the temperature in the Fahrenheit units is equal to 9/5 times the change in temperature in Celsius units. So that's kind of like, that's nice, right? That kind of like makes things a little simpler. Okay, so if you're dealing with the change in the temperature, you can ignore the offset. Okay, so one thing I like to do is do I know whether I've got my formula correct? One thing I've kind of committed to memory is that 37 degrees Celsius, which is a really hot day, is around about 100 degrees Fahrenheit. Okay, so convert 37 degrees Celsius to Fahrenheit. We're just going to plug it into the formula and try not to make a mistake. So degrees Fahrenheit is 9/5 times degrees Celsius plus 32, and when you do the math on that, you end up with 99 degrees Fahrenheit. And it's always nice to put a box around your final answer so I can grade your work correctly. Now, this is interesting. The size of a Kelvin unit is the same as a Celsius unit. So if the temperature changes by 5 Kelvin units, so the delta there is going to be 5 Kelvin, what we will see, going from minus 263 to minus 258, is that the difference there is, you guessed it, 5 degrees Celsius. So that's cool, right? So, the change in the Kelvin scale is exactly the same as the change in the Celsius scale. Where the two scales are different is in the 0 points. And the 0 degrees Kelvin is equal to minus 273.15 degrees Celsius. So your relationship, which is probably the one that you're going to use most commonly for converting from Celsius, which is what we like to measure things in, and converting it into Kelvin, which is what we like doing calculations in, is you just got to add 273. And if we wanted to go from Kelvin into Celsius, we would take away 273.15. So it's pretty easy, right? And then just keep in mind that the change in Kelvin units is exactly the same as the change in Celsius units. So it's really easy. Okay, so very common thing to be doing is to be converting Celsius to Kelvin, all right? So degrees Celsius here, 372.35. If you want to convert that to Kelvin, what do we know is that we have to add 273.15 to get it into Kelvin equals Kelvin. All right, so very, very simple. So Kelvin is equal to 645.50 Kelvin. Okay, so not too hard. The other formulas, like I said, this is an online course, so you can just kind of like write them down. You can just keep them handy. That's why it's good. It's really important to do those notes well. Okay. So we talked about some derived units before, and one of them we talked about was the idea of area. And area is the amount of surface that an object has. And you've probably learned some formulas for calculating the area of different objects. So for an example, a square, its area is given by the product of the length of its side. For a rectangle, the area is its length times by its width. For a circle, its area is pi times by its radius squared. And for a triangle, the area is 1/2 the base times the height. These formulas are not so important. They're good to know. You should know them if you have the math that you need to take general chemistry. But what's important here is that we're always going to be multiplying a length by a length when we're calculating the area of an object. So the units for area are always going to be length squared. So things like centimeters squared, millimeters squared, feet squared, miles squared, whatever your unit of length might be, area always has units of length squared. Now, what is volume? Volume is the measure of the amount of space that an object occupies. And if we look at the formulas for volume of common objects, we see that the units for volume are always going to be length cubed. So things like centimeters cubed, feet cubed, miles cubed, inches cubed, kilometers cubed, whatever, it's always going to be some length cubed. Okay? And you can look at all of these formulas, and if you were to think about the units here, you would come to the conclusion that it's always going to be 3 lengths being multiplied together. So that's how things are meant to be. So in the International System of Units, the base unit for volume would be the meter cubed, right? So meter cubed. Now, how big is a meter cubed? Well, it's huge. It's the size of a cube that is 1 meter. I'm not very good at drawing cubes, am I? 1 meter on a side. That's massive, right? That's 1,000 kilograms of water. So the cubic meter, which is the SI unit of volume, corresponds to the volume occupied by a cube with a side of 1 meter. That's really big and is far too large for most chemistry applications. Generally, we're going to be dealing with objects that are the size of sort of like decimeters cubed or centimeters cubed. So, we're not going to be using meters cubed for our volumes generally. The other thing that kind of makes volume a little weird is typically chemists will use non-SI units, and in particular we like to use the litre and the milliliter to measure volume. So what the heck is a litre? Well, a litre is the volume occupied by a cube with an edge length of 10 centimeters, or some people will say with an edge length of 1 decimeter. So a litre is just the volume of a cube that is 10 centimeters by 10 centimeters by 10 centimeters on each side, or it's the volume of a cube that is 1,000 centimeters cubed. Another way of saying it is it's the volume of a cube that is 1 decimeter on each side, so that would be 1 decimeter times 1 decimeter by 1 decimeter, or it is 1 decimeter cubed. So we've got a couple of things here. A litre is 1,000 centimeters cubed, or 1 decimeter cube. Now, we did mention that chemists like to measure things in milliliter, so it's worth thinking about how big is a milliliter. Well, in 1 liter, there are 1,000 milliliters. So, and we also know that there are 1,000 centimeters cubed in a liter. So you can see pretty quickly that 1,000 milliliters is equal to 1,000 centimeters cubed, or a milliliter is exactly the same thing as a centimeter cubed. So let's just kind of write some things here. 1 liter is exactly the same as 1 decimeter cubed. And then the other thing that's worth noting is 1 milliliter is exactly the same as 1 centimeter cubed. Okay, so how big's a liter? Imagine a cube that is 10 centimeters on each side. That's a liter. It's about a quart. The other unit that we'll see is the other quantity that we'll see is the density. And the density is the ratio of an object's mass to its volume. So to calculate the density of an object, we take its mass and we're going to divide by its volume. So mass has units of things like kilograms, grams, milligrams, micrograms, things like that. And then what's volume going to be? Well, it's going to have units like liters, milliliters, centimeters cubed, decimeters cubed, perhaps, etc. Right? So here's a typical density. It says a sample of seawater has a density of 1.03 grams per mil. So what does that mean? It means that every 1 milliliter of seawater will have a mass of 1.03 grams. So an alternative way of writing that density and it's exactly equivalent, is to write that you get 1.03 grams per 1 milliliter. Now, why do people make this little shortcut here of missing out, not writing it as a fraction and missing out the 1 there? And the main reason is because it's like more difficult to enter into a computer, right? When you're writing it out, you can do this if that makes more sense to you. Now, later on, we're going to learn that density is going to be used to convert between the mass of an object and its volume. I should say volume there. Okay. So we're going to kind of use the density expression to allow us to convert between mass and volume. Okay, so a few qualities of density. An object will sink in a fluid it is more dense than. So when snowflakes fall through the atmosphere rather than floating, that it tells you immediately that a snowflake is more dense than the surrounding air. Okay, when you throw a pebble into a lake and it sinks, it tells you that the pebble is more dense than the lake water. So that's an interesting thing to know. Now, if an object is less dense than a liquid, then it will float in that liquid. So if you throw a piece of cork into a lake and it floats, you know that the cork is less dense than the lake water. Or in this case, someone has discovered that the number 3 ball from the pool table is less dense than mercury, which is being used to fill the pint glass. Okay, now this is really weird because somebody took an entire pint of deadly mercury into a bar in order to demonstrate this principle, and I sure as heck hope that no one got to drink from that glass afterwards, because mercury is really, really bad for you. Now, I can hear everybody saying it, sitting at home saying this. What happens if the object and the fluid have the same density? Well, in that case, they'll do this thing where they remain stationary. So whatever height you set the object in that liquid, it'll just stay there. It'll neither sink nor rise. So if the liquid and the object have the same density, you can put it anywhere within the liquid and it'll just stay there. It won't float up, it won't sink down, it'll stay exactly where you put it. So that's kind of interesting, right? So it'll just stay stationary. So that's kind of cool. Okay, so that brings us to our to the end of our section on units of measurement. We're going to revisit this kind of again and again and again, and so I hope that this was helpful.